that was good. All right, so my diameter here and cross-sectional area is 4,107. And that's C mils. There is square inches, but I'm not going to write it down. And then I find out it weighs 12.43 pounds per 1,000 feet. So 1,000 feet of 12 gauge wire weighs 12.5 pounds. Not too bad when you consider what goes through the wall actually has 3 wires. So it ends up being 36, 40 pounds. You can pick it up and carry it around, but it's not quite as easy as just grabbing it. All right, so let's talk about a couple of things going on here. First of all, what's this whole C-mil thing? Conductor size. This is a pretty common industrial thing. So here's a conductor. You know, I should have picked which. I don't know what size this is. 0.1019 inches. Oh, 10 gauge. So I get some 10 gauge wire, and the example in the text is it's about 1/10 of an inch across. If I want to find the area of this, we're plugging into my equation. Area of a circle is pi r squared. Area is pi 0.1019 inches. Divided by 2, because that's the diameter, and this is the radius. Be careful. That's one of the biggest issues I see students do this. They get going on this, they're moving fast, and then they forget, oh yeah, they give me diameter and not radius. So I plug this in and go at 0.1019, divide by 2, square it, multiply by pi, and I end up with 0.008155. My decimal points don't go up quite as far. 8155 units, inches. Well, now I got square inches. So I can calculate my area, and now I can come put it in this equation. Now this isn't a real simple number to use, and if you got to do a bunch of these, it's kind of a pain. So we actually measure with something else. I think we talked about this last semester too, but I don't remember that. So what I'm going to do is I'm going to come back in and I'm going to go across this and I'm going to measure it and I'm going to say, okay, you know what? This is 101.9. And let me write it further over some space. 101.9 mils. Okay, a mil is 1,000th. Millionth of an inch, right? 1,000. Yeah, move the decimal over 3 spots. It's an industrial measurement. We want to measure small things. Rather than trying to measure them in inches and end up with these really awkward numbers to work with, we just use a different scale. So there are 1,000 mils in 1 inch. Now, if I go down and I calculate area is pi r squared, area is pi times 101.9 mils divided by 2 squared. I end up with that same looking number, except for a different decimal spot, square mils. But I decided to get even smarter about this stuff and say, you know what? All my wire I'm going to use for but this stuff's gonna be circular probably. So I could do this. I can look at this and say, if that's circular and it's 1 mil across, then I'm gonna say it has an area that is so I have two choices. I can write it as 0.7854 square mils. Do that calculation just like that. Or I can look and say, 1 mil across, I'm just going to call this as 1 rather than square mils, C mil. That's what a C mil is. It's a circular mill. So conveniently, I can just go, it has a diameter of 1, it's 1 circular mill area. It's also stay consistent, my units everywhere. And that's what I put in my table. Note, if I had a square conductor, which I can certainly have, that's 1 mil across, if I went and found the area of this, that would be 1 mil squared, or 1.273 C mils. But I'm usually going to have a circular. If I take one and I go, hey, what about this? This is 2 mils. My area is 4 C mils. My area still goes up as the square of my diameter. So I have some problems this week. Here's the thing in it. You're probably gonna have area in C mils, or find it in C mils. And then you're going to go into this table, or you can use this table to relate anything you're given in the problem, from diameter, to area, to size. Or we may have problems where we have you calculate, oh, we need to figure out how much wire what kind of wire we're going to use to make this safe. So we know how to do our area now. We'll come back and work with it. So let's try doing something in the problem. Okay. You understand what I'm doing on this? It's probably units you haven't used before. Frankly, it'd probably be easier on you if we use meters and square meters. But once you get into certain work, my guess is most things will be set to, you'll be told gauges to use. And just so for reference, okay, wiring in the wall, 1412 for household wiring, probably more like 1210 for industrial wiring a lot of times. And then the high power in your house will probably be for like electric stove or something, probably 10. Be 8, but probably 10. The small little wires we use in here, I actually don't know what gauge they are, but they're probably somewhere around 22, 24, 26, somewhere in that range. If you're inside a piece of electronics and it has some power, it's probably going to be something like 18 gauge. This also does not address the fact that it's a separate issue, that most wire you're going to use inside, well, those little jumper wires are single strand, but a lot of times for connection wires for higher power, you'll use stranded, a whole bunch of stranded. Area still measured the same, total area across it. All right, so let's take a look here. So I have 230 volts. That's my supply. And now I've got to run a wire out to a load. Okay, now I'm going to do the following. So I'm on the whiteboard. I can come in and say, you know what? This wire already knows 2,300 feet long. I know that this load requires 220 volts to operate properly. Now, if I were just setting this up in an idealized situation, I go, no problem. I got wire that can just carry whatever, because it's zero resistance, right? No, it's not. It's 2,300 feet long. Not only that, this thing needs to carry 25 amps. Okay, this is like a big motor or something. So I'm going to go in and do the following. I'm going to put a little resistor in here. And acknowledge that, you know, I don't have a spot where I can just assume my resistance is zero. So first of all, what I could do is do the following. I have a lot of ways I could go about figuring something out, but maybe I'm going to look at this and say, you know what? I need 220 volts down there. I have 230 volts here, no problem. That means I can drop 5 volts here and 5 volts here. Don't forget, you have to drop in both directions because you're right, it's 2,300 feet on both sides. All right, so if using Ohm's law, all the stuff I introduced today, I don't even need to get into detail, right? Ohm's law is the voltage over the current. If I'm dropping 5 volts and I have 25 amps going through it, what's my resistance? What's 5 over 25? 1/5. Yes. Which is 0.2. So I need wires that has 0.2 ohms. So the next question is, what do I need? So we decide, you know what? I'm running this out. 10 gauge is pretty thick wire. So I'm going to do this. My first attempt is going to be to try 10 gauge wire. If I use 10 gauge, I can guess I'm going to try it. I said first attempt. It's not going to work, but we're going to try it. So, what's the resistance of 2,300 feet of 10 gauge copper wire? So we know the resistance is the resistivity times the length over the area. Length is 2,300 feet. The area is, oops, I didn't write it down. That's a 14 gauge written there. I'm not sure how I got the order of the notes or where I did, but there's this whole thing in between. So I go look up that super big table we had. And again, you have this right in the text. 10380. So it's 10,380 C mils is the area. Now all I need is resistivity. Now I have another table. I believe there's just a section apart in the text. Another table. Okay. It has a whole bunch of different types of materials in here. I look at iron, nickel, zinc, tungsten, copper, silver, gold. It'll tell me whether it's an alloy or an element. It'll tell me ohm mils. So, resistivity for copper is 10.09 ohm C mils per foot. Okay, again, my length is 2,300 feet. My area is whatever number I had over there, 10,380 C mils. So now I can go back to my resistance. Resistance is 10.09 ohm C mil per foot times 2,300 feet divided by my 10,380 C mils. When I'm done, my resistance is going to be what? Drum roll. So 10.09 times 2,300 divided by 10,380. 2.24 ohms. That doesn't sound like too bad a resistance when I just looked at it on its own, does it?
Won't that not work though?
What?
Because doesn't the wire need to have 0.2 ohms?
Yeah, it's still too much.
Yeah, okay.
You're right. And that's just one direction. So go back to my circuit. And I have 2,300 volts. And I have a resistor that's 2.24 ohms. And I have my load over here. Okay. Now I don't have a resistance for the load, so we're just going to say, hey, remember how we said we need 25 amps? Let's just see what happens if we're drawing 25 amps. So I can take 25 amps times 2.24 ohms and find I drop 56 volts. Which means I'm going to get something like 118 volts here. In reality, I probably won't draw that much current, but I also won't get enough voltage on the other end to do anything. So I'm going to hook it all up, and I'm going to draw a bunch of current. My wire's going to get warm, and my load's not going to do anything. Oh, well, hey, maybe we need bigger wire. So a couple questions real quick before we go on. Why didn't we just get like really, really, really thick wire to start with without doing calculations? I mean, because it weighs more and it costs a lot more, you know. So, you know, this 10 gauge, I can still roll the whole thing out by hand for sure. Good. All right, so let's try it from the other direction. I'm going to erase this bit if you're okay with that. Let's try it the other way. Let's say, all right, well, hold it. Let's see. This was a bad idea. Picking the gauge, there is a time when people start getting an intuition, but it can be dangerous. So let's try it the other way. Let's try it this way. Resistance equals rho L area. Okay, it's definitely copper. We'll talk about different materials and resistivity in a second. The length is set. We said, oh, it's got to be 0.2 ohms. So I can solve for area, right? So area is going to equal rho L over R. Right? I multiplied both sides by area over resistance. To isolate area.
Yeah.
I know. That nasty algebra. And now, 10.09. Ohm feet per C mil. Length is 2,300 feet. Resistance is 0.2 ohms. When you do these, you can always check your units too, because you can do algebra to them. Ohms divided by ohms. Oops, this must have been C mil per foot. Feet over feet. Yeah, it's easy. So I'm left with so many C mils. All right, so area. 10.09. Times 2,300 divided by 0.2 is 116 0.035 C mils. So I need something that has an area of 116,000 circular mils or more. So now I return to my handy dandy little table that I was just on. I really like these notes, but I should pull them up, put them in a little bit more. And I look up this table, I start looking for the cross-sectional area, and I find 105,500. Oh wow, this is thick. So I go up here, and I find up here something. 105,500. The next one is 133,100. And I look over here. This is labeled 1O. This is labeled 2O. So I want the thicker one, so it's got a lower resistor. That means I actually need double-aught wire to carry that. I look way over to the side, double-aught wire weighs 400 pounds per 1,000 feet. So at 2,300 feet, I'm going to be up pushing probably 900 pounds or so of wire. So that's why I didn't go there initially, because I thought, I don't need that much, but I do. So I'm probably not going to roll this out by hand. Stretch it out by hand. All right, so I want you to work through a few of these calculations. It just gives you a little bit of feel. We won't do a ton of these, but we'll do some. We talked about this again in the intro course, so let's see if you remember. When I look at the little resistivity table, you remember there's an element that's actually got lower resistivity than copper.
Silver.
Yeah, silver, the least resistive element in nature. Why don't we use silver wire?
More expensive than copper.
It's more expensive and it actually has a physical property that we don't want to use too. Pure silver is very soft. Try to stretch wires and they break. So we need something. So our wiring needs to have something that's rigid. I think I mentioned again because I had all the audio people that ask you. Gold is something you buy gold-tipped connectors for all kinds of things. If you go to the store, half the time the salespeople will say, "Oh, it's because it conducts better." I look at my little table; it doesn't conduct better. It doesn't conduct as well as copper. So the question is, are they selling you snake oil? Hey, put gold bling on your connectors and it will be better. Or is there a reason for it? There is arguably a reason. Yeah, any good ideas? Or gold is inert, so it doesn't react to the atmosphere. It doesn't corrode over time. Copper corrodes. You've seen copper statues or bronze statues, which is copper alloy, and they get that green patina. But it's that's because patina is supposed to be when stuff looks old, worn out, because it's considered attractive. But anyhow, so copper naturally has some corrosion in it, and that corrosion doesn't conduct. Now the irony is the only place I've ever seen those copper connectors are for high-end audio that people buy to put in their houses that has climate control. Never seen anybody use it for things like exposed to the elements or anything. So, it leaves it up in the air. So I don't really know the truth, but and we don't put that on any of our stuff. Our wiring in our house and wiring everywhere is just copper connections. You keep it covered with an insulator to protect the copper, but also to not shock things. Aluminum has a conductivity that's almost as good as copper. In fact, we used it for wiring houses for a while. We had a lot of aluminum around and not so much copper. And the biggest issue with it is when it overheats, it catches on fire, whereas copper tends to overheat. the other things on fire. And when the two come together, they actually have a weird corrosion. So there's a certain method you have to go through and connect them. So we don't use it much anymore. So yeah, at the end of the day, we use copper because it's actually a very good conductor, but it's also one of the, I don't want to say it's one of the best, but it's one of the good conductors that's not super expensive. But it's also physically tough, but not so physically tough that we can't work with it. If you did solid steel conductors everywhere, and not only does it conduct quite as well as copper, but it's a lot hard. If you had a 14 gauge copper wire, you can bend with your hands pretty easily. If it was a 14 gauge steel wire, you would need a pair of pliers and two hands and a lot of proof. All right, so the reason I mention all that stuff is we need to keep it in the back of our mind. I mean, we're dealing with real stuff. People make decisions on what we're going to use, not based on, oh, I just looked up at a table, it's a good conductor. Anyway, I went, what stuff can we really use that really connects, that really lasts a while, that's physically strong enough, but cheap enough, not too expensive, and this whole list of things that are not just about its ability to conduct. Okay, so resistivity. Let's take a look at, you know what, I might let you work it, but I'll talk you through it. This is a problem, again, I think I had you do last semester, so I do a fair amount of those. It's like, let's hit a little review of what we did last semester to make sure it's down. And what I do is I give you a circuit like this, and I say, here's a conductor, here's a conductor. Now really, that's my load. And this is the resistor of the wire. And what I ask you is how much power is delivered to that load. So to solve this, all I got to do is go, oh, this is just a series circuit. My resistors in series, and I can find my total current, use my current to find the power being dropped across the load. And I can find the power being generated by the battery and figure out how much power I'm losing in the wire as I transmit my current from one end to the other of this long wire. And then I go back and say, hey, if it's an ideal case and these don't lose anything, how much power would I transfer? So just do those calculations. Or I might ask you, what gauge wire would you need for this to be true, or something like that. So let's just go through those and do some calculations on the homework. Review fuses and breakers, those are in here. Okay. So I'm done with that because I want to just spend time working on some stuff. This week's lab is a little different. And unfortunately, there's a little thing we have to figure out how to work through. What I do this week is I give you a whole bunch of circuits work that you've already built this semester. And what I'm going to have you do is go off and use a simulator to simulate them. The one I tell you to use is multi-sim. I really like it. It's fun. We used it last fall. I developed this for it, and it works really well. Here's the problem with multi-sim. Somewhere at the end of last semester, they significantly reduced its ability for the free version to do stuff. And because I have so much stuff saved in it, they blocked my account from me, so I can't go back and try. I need to go pay them, but I've been meaning to send something off and look what I can get for like a little license for the school or something. So there is still a free version of it, and I think it will do absolutely everything you need for this class. So go try. Sign up, search for multi-sim. It's out there. You can do this whole lab at home too, because it's all simulation. There are a couple other simulators out there. Circuit Lab. If you want to play with any of these, let me know. I think I already showed you the Fallstad, which you can use. I just opened one called Every Circuit this morning. that I was playing with when we started. These all have free versions online. This one I was working with because I want to get it where it's done by a parts company. So they're really happy to put up a free simulation software that links to their parts. I just couldn't get it to work this morning. Fallstat's the older one. I think I pulled up like a lot of the digital stuff last semester for you guys on that. Shouldn't do that. But it'll do everything. Every circuit has open this morning. It looks pretty, but I haven't used much. It actually looks like an updated 2020 version of Fallstat. But multi-sim works great. So go ahead and try to sign up for that. I think it'll only let you save 4 circuits, so maybe don't try saving them. Set it up and run it. I can help you. If one of you gets logged in, I can help you because mine won't open right now. I can't until I pay them money. I can't like open it and show you. But what you're going to do is you're just going to go back through series, parallel, the potentiometer labs, and build them. But not on a circuit board. You're going to build them and simulate them. Let me